Hello. We know that most of the problems in science and engineering can be formulated as differential equations. In numerical analysis, we have learned about the most widely used iterative technique known as Runge-Kutta method. Runge-Kutta method for differential equation is very commonly used in many textbooks for solving first order differential equations. In this session, we are going to see how the Runge-Kutta method is applied to solve a second order differential equation. We have the question, use the fourth order Runge-Kutta method to compute the value of y at point 2 given that d square y by dx square plus y equal to 0. Given the initial condition y at 0 equal to 1 and first derivative of y at 0 equal to 0. We know by Runge-Kutta method y at a point 0.2 can be found out using the formula y0 plus 1 by 6 into k1 plus 2k2 plus 2k3 plus k4. Since the equation is a second order differential equation, our first attempt is to change it to a first order form. So let's consider dy by dx is equal to z, and we consider this as a function f, which is a function of x, y and z. Then the given differential equation can be written as dz by dx plus y equal to 0, which we can write as dz by dx equal to minus y, and this we consider as another function g, a function of x, y and z. And apart from the wave function f of x, y, z, using which the k values are calculated, here consider one more function g of x, y, z and calculate the corresponding L values as we calculate the k values. And we know that from given initial conditions, here x0 equal to 0, y0 equal to 1 and z0, which is the initial value of the first order derivative of y, and given as 0. And since we have to compute the value of y at point 2, we can consider h as 0.2. Now first we calculate the value of k1, which can be computed as h into f of x0, y0, z0, and putting the initial values of x, y and z, we get the value equal to 0. Similarly, we can calculate the value of L1 using the function g, and this the value turns out to be minus 0.2. Then we calculate the k2 value as h into f of x0 plus h by 2, y0 plus k1 by 2, z0 plus l1 by 2, and substituting the corresponding values we get the value minus 0.02. Similarly, we also have to calculate the value of L2 using the function g, and we get the value equal to minus 0.2. We also have to calculate the value of k3, whose value is f of h into f of x0 plus h by 2, y0 plus k2 by 2, and z0 plus the previous L value L2 by 2. And this value also turns out to be minus 0.02. Similarly, we also calculate the value of L3 using the function g, and this is found to be minus 0.198. Again, we have to calculate the k4 value also using the relation h into f of x0 plus h, y0 plus k3 and z0 plus l3, and this value is found out to be minus 0.0396. Now we have to incorporate all these found out values of k1, k2, k3 and k4 into the final equation to find y at point 2. Incorporating these values, We find the value of y at point 2 as 0.980067. This is the final result. Thank you.